NASA has confirmed that several plane-sized asteroids are making close approaches to Earth this week, including one known as 2025 YH6. While the distances involved may sound small on a cosmic scale, scientists say there is no risk to our planet. These flybys are part of routine monitoring by NASA's near-Earth object tracking systems and provide valuable data on asteroid motion and orbital precision. In this video, we will explain what was observed, why it matters scientifically, and what happens next. Let's get started. NASA's Center for Near-Earth Object Studies, working with the Jet Propulsion Laboratory, has been tracking a group of near-Earth asteroids making close passes within a short period of time. The largest of these is asteroid 2025 YH6, estimated to be about 230 feet in diameter. It is moving through space at roughly 20,000 miles per hour and will pass Earth at a closest distance of approximately 1.26 million miles. From an observational standpoint, this qualifies as a close approach, but it remains well outside any region of concern. The object's size makes it relatively easy to track, allowing astronomers to calculate its orbit with high precision. What stands out this week is not a single asteroid, but the presence of several plane-sized objects passing Earth within days of one another. Alongside 2025 YH6, NASA is also tracking 2025 YK6, a smaller asteroid measuring about 73 feet across, which is traveling significantly faster and will pass at a distance of over 3 million miles. Two additional asteroids, 2025 YIZ4 and 2025 YQ5, are also scheduled for close approaches, ranging from roughly 1.8 to 3.4 million miles from Earth. All of these objects were detected through a global network of automated sky surveys and ground-based telescopes. Once an asteroid is identified, repeated observations are used to calculate its trajectory. Each new measurement refines the orbit, narrowing uncertainties and improving long-term predictions. By the time close approach updates are made public, these objects have usually been tracked for weeks or longer. The announcements often coincide with the moment of closest passage, not with the moment of discovery. In this case, the orbital data show stable trajectories that do not intersect Earth's path. In short, these flybys are not unfolding events. They represent the final, most precise phase of a monitoring process that is already well underway. Although none of the asteroids involved pose a danger, close approaches like these are scientifically valuable. They provide real-world opportunities to test how accurately near-Earth object models perform under observation. Asteroid motion is governed primarily by gravity, but over long periods, smaller forces also play a role. Effects such as uneven heating by sunlight can gradually alter an asteroid's orbit. These changes are subtle, but they accumulate over time. Tracking objects like 2025 YH6 across multiple observations allows scientists to detect and account for these influences. These events also demonstrate how impact risk assessments evolve. When an asteroid is first detected, early calculations often include small uncertainties due to limited data. As additional observations are collected, those uncertainties shrink. This process explains why some objects briefly show non-zero impact probabilities before later observations reduce those values to zero. A recent example is asteroid 2024 YR4, which earlier this year briefly registered a measurable probability of impact decades in the future. Follow-up observations later confirmed that it poses no risk. This sequence is expected and reflects improved data quality, not increased danger. The term potentially hazardous asteroid is frequently misunderstood. It does not imply an imminent threat. Instead, it refers to asteroids above a certain size whose orbits bring them relatively close to Earth's orbit. Many of these objects remain on stable paths for thousands of years without ever approaching Earth closely. None of the asteroids involved in this week's flybys fall into a category that requires heightened concern. Their orbits are well-defined, and no long-term impact scenarios are being evaluated. Beyond risk assessment, these objects are remnants of early solar system history. Studying their sizes, velocities, and orbital characteristics helps refine models of how near-Earth object populations form and evolve. Each well-tracked flyby strengthens confidence in those models. For scientists, the value lies not in how dramatic a flyby appears, but in how precisely it can be measured and predicted. After these asteroids pass Earth, there will be no alerts, warnings, or follow-up actions related to them. Their trajectories are already well understood, and no future close encounters of concern are expected. What continues, however, is the broader effort to improve detection and monitoring of near-Earth objects. NASA and its international partners are expanding survey coverage to identify smaller asteroids earlier and track them over longer periods. Future ground-based systems and space-based infrared observatories are expected to reduce remaining blind spots in near-Earth space. Early detection is critical. The more time scientists have to study an object, the more accurately its future motion can be predicted. Even modest increases in warning time dramatically expand the range of possible responses should a genuinely hazardous asteroid ever be discovered. There is also growing emphasis on understanding asteroid composition. Size alone does not determine risk. Density, structure, and internal makeup all influence how an asteroid behaves, particularly if deflection were ever required. NASA's DART mission demonstrated that altering an asteroid's orbit is technically possible, but such efforts depend heavily on knowing the object's physical properties. Another important aspect is communication. Near-Earth object data are now published openly and updated frequently. This transparency allows the public to see how predictions evolve and helps prevent unnecessary alarm when close approaches occur. Events like this week's flybys highlight that Earth exists in a dynamic environment. Small celestial bodies regularly pass through our orbital neighborhood. What has changed over time is not the frequency of these encounters, but our ability to detect, track, and understand them with precision. The recent asteroid flybys show routine monitoring working as intended. Their paths are well understood, and none pose a threat to Earth. What's changed is not space itself, but our ability to track it with precision.